still going to talk about the James-Cummings model and some solutions we can get out of the model. And I'm going to review for you what we did at the end of the last lecture, which was solving the James-Cummings model for the simple case of coupling to a number state. And then using that, we can come up with a very simple scheme for entangling two atoms using the optical cavity. And then we're going to look at a different way of solving for the James-Cummings model, which is by finding the eigenstates. And then quantum mechanics tells you that once you found the eigenstates, you can basically expand the initial state onto the eigenstate at some time, attach the characteristic time evolution dependence, that exponential factor, to each of the eigenstates, and then find the time evolved version of whatever state you have. So that gives you the dressed state. Okay? And then using the stressed state, we're going to compare to the previous case. In the case of we're going to compare and recover things like gravity oscillation in the case of not exactly resonant cavity atoms. Okay? And then we're going to look at collapse and revival, something that happens when the atom is coupled to a coherent state in the cavity. And also we're going to look at what happens when the atom is coupled to a thermal field. Okay, so previously we talked about this James-Cummings model. This is a recap from last time. Okay, and the Hamiltonian looks like this. We write down the atomic part, which is by choosing the zero of energy, we should write it like this. But, and then the field part. And then there's this interaction part. And then the first step we did was we extracted. Okay, so the Hamiltonian can also be written in terms of some constants of motion. We extracted the constants of motion. Wrote this part consists of the constants of motion, which one thing is the number of excitations in the cavity, the other thing is the number of electrons. So that's the constant of motion. And then what's left was this part. And this delta thing is the detuning factor. Okay. And we solved this problem for the case of no detuning. So when the atom is exactly resonant with the cavity. And we found that, okay, so the two states we were concerned with was so the atom being in the excited state and the field being in the number state n. And then this can be coupled by this Hamiltonian to atom in the ground state and field in the n+1 number state. Okay? And we considered the case where this is the initial state. Okay? And we derived the interaction picture, which says that all you need is actually this part, and in the case of no detuning, then this was the part that governs the time evolution. So the solution was that if I expanded psi of t onto these two possible bases, okay, so I used C excited as a function of t plus ground. Then we found that this was equal to cosine of lambda square root of n+1 t. Okay. And then this, by matching the boundary, by matching the initial conditions, this must have to be equal to minus I sine lambda. So this was the solution. So now we can write down the state at any time by just plugging these in. And it makes no difference if the atom started in the this initial state, right? Then you basically just exchange these two solutions. Okay. So now a comment here: when there is no atom, there's no field present in the zero photons present in the cavity, then we can see that the atom still evolves, and it evolves in a cosinusoidal or sinusoidal fashion. And we can define something called the population inversion. Okay, so this is typically denoted by W, and this is of course a function of time. And this is the population inversion is the expectation value of this operator. And it's kind of apparent why this is defined so, because sigma 3, when written out in the two-state representation, this is correct? Okay. So if you were to find the expectation value of this is saying find the probability amplitude to be, the probability to be in the excited state, subtracting the probability to be in the ground state. Okay, so if we were to evaluate the population inversion for this thing, okay, obviously, what are you going to get? The E and N are orthogonal to each other. Okay, and this one you're only operating with the atomic part. So think about it. Basically, you're going to get cosine squared minus sine squared. Right? Okay. So for the case of the coupling to the number state, you get that this is cosine squared lambda minus sine squared. Correct? Okay. Now, using simple trigonometry, we find that this is equal to cosine 2 and I think there should be a factor of, no, that's it. Yeah, maybe it's a 1 plus or something. Can't remember. No, that's it. Yeah. So what does this tell us? If I were to draw a plot, so if we started in the initial state, meaning that the atom was in the excited state. So, oh sorry, this should be minus 1. And 0, I set the 0 to here, minus 1 to here. Okay. So if I started in the initial state, meaning the atom is excited, then I basically undergo this cosinusoidal oscillation. And we know what this is called, right? This is Rabi oscillation. So the atom goes from being shortly excited to being shortly in the ground state, non-excited, in a periodic fashion. And we also had this for the classical case. Remember in one of your homeworks, I think you saw for the case of in the case of spin systems, there's no difference here. The spin is a two-level atomic system, and this is what you get here as well. Okay. But notice what does the special thing that quantum mechanics says is, even though there's no atom, there's no photon in the field, in the cavity, you still get this oscillation, and that was the vacuum gravity oscillation, which we ended with at the last lecture. Right. So this is what we get. So the quantum mechanics tells you that because of the presence of the quantum vacuum, even when there's no zero photon present in the cavity, because of the vacuum, you still get this oscillation. And what's important to see is that this oscillation frequency is dependent on this lambda factor, right? Which is to say how much. Remember, we defined lambda to be the magnitude of the dipole moment of the atom times the G factor for the field, right? Okay. Divided by h bar. So depending on the strength of this thing, this determines the frequency of the oscillation. And in the case of vacuum gravity oscillation, this is a 1. So this 2 times this is exactly the oscillation of the population inversion. So what this tells you is that if this was big, so if the atom was coupled strongly to the cavity, okay, then it is it more readily gives up its excitation. Of course, it also more readily accepts a quantum excitation from the field, right? But it tells you that this essentially what's happening here is in the case of a vacuum, the atom is just emitting one photon and absorbing it by itself at a later time. But it tells you that we can engineer how soon the atom emits and absorbs this photon by engineering this coupling constant. Okay? And this is one aspect of what's called the Purcell effect. So I think Purcell.
PU.
Oh, okay.
PUR.
PUR. ELL. Something like that.
ELL, yeah.
Purcell effect. Later, we're going to see a different version of this in the off-resonance case. But it tells you that you can engineer in a cavity. You can engineer how much the atom wants to emit a photon. The spontaneous emission can be engineered, and if this is for us when we're considering a lossless cavity, meaning that the cavity was terminated by perfectly reflecting mirrors. Now, it is also possible, now just based on a simple variation of this, if we had a perfectly reflecting mirror on one side, but on the other side we have some transmission. Okay. We have a maybe very transmitted mirror. Now, of course, the physics is going to change because once you introduce this transmission to the outside, this is no longer a closed system. And our Hamiltonian might not work like that. It's as simple as that. But what is possible in the experiment is to have a cavity that's very strongly coupled to this, and have and speed up this spontaneous emission process. Okay, so that's possible using this Purcell effect. And actually, Edward Purcell is tied to this campus. Virgil, do you know? Do you agree?
I don't know. How is it tied to this campus?
Not to our university, but he's actually a graduate of the high school.
High school here?
Yeah, the University High School.
Oh.
Yeah. Anyways, he went to Chicago. So that's the Purcell effect and vacuum gravity oscillation. Okay. So now we're going to use this kind of dynamics, to see how we can entangle two atoms together using a cavity. So,
Can you tell us what is frequency of oscillation is?
Oh, the frequency of oscillation is this.
So what do you get in real life? Gigahertz, megahertz?
Oh, I see. Well,
terahertz?
let me think. So I don't know. I never looked at that. It depends on it would depend on the dipole moment, how big the dipole moment of the atom is, and this can be pretty big for a Rydberg atom. And then it also depends on this G factor. I guess maybe something like 100 gigahertz or something.
100 gigahertz?
But I cannot back that up. I'm just
Okay.
recalling from memory. But you guys can look this up. We would need to find the, because what is G? G is like, it was related to the polarization of the atom, right? And then it was related to this thing, okay, which is h bar omega k divided by 2s. This is the compensation volume. And then you need to attach the spatial dependence of the field at this. If we take this to be 1, okay, and we take this to be a number between 1 and 0, or 1 and minus 1, something like that. Because when this started with the the direction of the atomic dipole, it's going to give you a cosine vector. It really doesn't matter. So I guess this is what matters. And so you can sort of, and this omega k needs to be roughly coupled to the transition frequency. And I'm saying this omega is roughly around 50 gigahertz-ish for a regular atom. Okay. So yeah, I'm not really sure what that is in real experiments, but you know, we can find out. Maybe I can tell you on next Tuesday. Okay. So anyways, so now we move on to this entanglement. Okay. So you've seen entangling in the context of spin systems. But in fact, entangling just means you have two particles or two degrees of freedom that's not separable. It cannot be factorized. For instance, you study the Bell states. Right? The Bell states. And we studied Bell's inequality and stuff like that. Right? One of the Bell states was something like this. Okay? So a state. Well, it was two atoms, or two spins. Let me write the case with two spins. You could have spin up, spin down, plus a spin down. So, or in the case of photons, it could be the horizontal or vertical polarization, and we studied that to look at Bell's inequality. Right? Well. In terms of spins, we could write this, and this is just a two-level system. Up spin could be replaced by the excited state. Down spin could be the ground state. Ground state, excited state. And then to be precise, let's label these. So this is for atom 1, atom 2, and atom 1, atom 2. Okay. So this gives you a Bell state. And the Bell state is clearly entangled, meaning that if I found atom 2 and I made a measurement as to whether it's excited or not, I can determine if I found it to be in the ground state. Then without measuring atom 1, I know for sure that it's in the excited state, because this is not factorizable. So let me show you how we can use that simple dynamics there to construct a state like this. So for that, we're going to have this set up. So we have a cavity. Cavity with two mirrors. And then these are the boundary. So we have two atomics, two atoms. And then I'm going to label some time, and I'll explain what I mean. Okay, so the field inside the atom roughly looks like this. It's like a Gaussian field. That would be the mode that's coupled to the atom. Okay. And then I call this time to be T0. Okay. This time to be T1, and also over here. And this is T2. And we call this being atom 2. One. Okay, so what do I mean with these times? Okay, so when this line crosses with the boundary, okay, over here, it means that atom 1 at T0 enters the cavity, and it leaves the cavity at T1. And simultaneously, atom 2 enters the, simultaneously, atom 2 enters the cavity, and it leaves the cavity at time T2. Okay, is this clear? Okay. So now I'm going to say that the atom number 1 was prepared to be in the excited state, and the atom number 2 is prepared in the ground state. Okay, to start with. And the field inside of the cavity is kept as the vacuum. So the cavity is in the vacuum state. Yeah. So if I were to write down, before anything happened, okay, before the experiment, the field was kept at the vacuum state, and then we prepared these two electrons, two atoms. Okay. So the total state before the experiment, okay, so before entanglement, I should say, before the experiment, we have excited state, ground state, and vacuum, right? Okay. So now let's consider what happens as atom 1 enters the cavity at T0. Okay. Once it enters the cavity, okay, because the cavity is at 0 and the atom is excited, there is a chance for the atom to transition and give off one photon to the cavity, right? So according to this. Okay. So this state is clearly linked with this state by the James-Cummings dynamics. And we can write down at any time, given this initial condition, we can simply use the Rabi oscillation formulas. We can write down that at any time, okay, this state is going to evolve, okay, into cosine of lambda t, because we know that it's in a vacuum, right? Times Can everybody see this? No problem. Okay. So this is the evolution. And now if I were to write down the whole thing, up to now, atom 2 has experienced nothing. So if I were to write down the whole state, I simply just attach it. Right? So I could attach the ground state of the second atom here, but let's not do that. Okay, so specifically at time T1, right, I just simply replace T1 here. Okay, so this is evolving from T0 to T1. Okay, and now by choosing how much time the atom spends inside of the cavity, and we can do that by simply choosing engineering the velocity of the atom. That's not very easy, but theoretically it can be done. So I can choose lambda T1 to be equal to pi over 4, simply by choosing the velocity. Yeah, but I'm just, okay, T0 is 0. Okay, so that's why it's T0. Okay, so by choosing this, then the state that evolves to is 1 over square root of 2. Right. Okay. So this James-Cummings dynamics, what it does is it entangles the first excited atom to the cavity. Entangles atom 1 to the cavity. Okay. So this is what happens at T1. So now, simultaneously at T1, okay, the second atom enters the cavity. So it's no longer just in the ground state. Something is going to happen to it. Right? So now I attach the second atom. Okay. So simply by up to T1, the second atom is completely factorizable from the other two. So the second atom when attached would be T1, T2, 0 minus I. T1. Correct? This is at time T1. So now, for this part, so right now the atom 1 has already left the cavity, so it's going to keep what it is. Okay. For this part, can the James-Cummings Hamiltonian do anything to this part? No, right? Because there's just no energy available for interaction. So this part stays. But what about this one? Okay, this one, according to the James-Cummings model, this is like sending in an atom initially in the ground state and having one photon in the cavity. So the James-Cummings model is going to act and entangle this one. Okay, so this becomes what? This is going to be cosine of lambda. This at time T2. Okay. T2. And then T2 1 minus I sine lambda T2 excited state. So this becomes this. Square root of 2?
Because you have 1.
Oh yeah, there should be a square root of 2, sorry. Yeah, you're right. Thank you. So cosine is square root of 2 lambda T2 G2 1 minus I sine square root of 2 lambda T2. Okay, so now I can once again choose the velocity of the atom. Okay. So let me set. So now set. Okay. Square root of 2 lambda T2 to be equal to I'm going to multiply over 2 this time. Multiply over 2. So make the second atom slower. Alright. And then what happens? Cosine pi over 2 certainly goes to 0. So we're just left with a minus I E2 0 thing, right? Yeah. And then this minus I, when it sees this minus I, gives you a minus 1, right? Okay, so actually we were constructing this thing, sorry. Yeah. So then at time T2, the entire state goes to what? It's going to be 1 over square root of 2. Excited state of the first atom, G2, 0, minus G1, G2, at time G2. Okay, so now you notice that the state of the cavity is completely factorizable from this product, right? So, question?
Is there any well-known method to set this velocity in practice?
That's there is, okay. And the method is by using some lasers, but it's very complicated, and I don't want to go into detail here. Later when we actually consider some more realistic, because right now this is very ideal. Even if you could control the velocity of the atom. How do you make sure that this leaves the cavity as soon as this enters? You can't.
Exactly.
Okay. So what you can do though is, remember that we're just working with a two-level system, and any implementation of the two-level system have this potential. And there are certain two-level systems that's very suitable for this, and I'll explain in a minute. Okay. So now this is factorizable, and we basically construct one of these Bell states. Okay. So now getting back to his question, it's certainly very hard to tune this if we were actually using atoms. Okay. But now, since the James Cummings model just tells you so long as you have a Hamiltonian that looks like this, doesn't have to really be atoms and fields. What we've done so far is just look at the mathematical model. Whatever implementation have that potential to entangle two things. So let me tell you what can do this a bit easier. And this is the getting back to the Cooper pair box. Okay, so the Cooper pair box, what it does is it's also kind of like a two-level system. Okay. Two levels being, so the Cooper pair box looks like this. So you have something called the reservoir. And then there is an island. Okay. And,
Can you press harder the blackboard? Right? Press
Oh,
hard, otherwise
okay.
it's hard to see from the back.
All right. And this is connected to some external source. Okay, so what this is, this part is superconducting. Okay, this part is also superconducting. Okay, and then this insulator here. So this forms a Josephson junction, as we talked about, SIS interface. And we know, and this junction over here, it has a. I'm going to call this CJ. Okay, so it has some capacitors. And then the island is also connected to external circuit by another capacitor, which we will call the gate capacitor. Okay. So what's going to happen here is that based on the number of Cooper pairs inside of this island, okay, so the island two things can happen. You could charge this thing up and have so many electrons inside of this island. Okay, and we know that there should be Cooper pairs because everything is superconducting right now. So you can control the number of Cooper pair blocks by tuning this voltage appearing at this side. Okay, but then because of the Josephson effect, we know that there is a chance for the two sides, the island and the reservoir, to exchange Cooper pairs. Right. So in some situations, okay, you form a two-level system by saying that, okay, so I have one level is I have one Cooper pair inside of the island, and another level is that I have 0 Cooper pair in the island. Okay. So what happens is, so maybe we can say that the excited state, sort of, and the ground state, okay, meaning one pair in island, and 0 pair. Okay, so essentially, the Cooper pair box is one realization of a two-level system. Okay? And by coupling the Cooper pair box to an external cavity, okay, and that cavity is realized by a coplanar waveguide, and it's in this fashion. Okay, so we have some microwave strips like this. Okay, and then there's some capacitance here. Okay, so we have capacitance at these two sides and some inductance here. This is like an LC resonator. Okay, and when we have an LC resonator, we can also quantize the field, much as we did like in the free field case. So what happens here is, okay, roughly speaking, we know that here is going to be like a maximum of the current, because if I were to quantize the field, the voltage will look something like this, quantitatively speaking. If I was to think about this as a cavity, okay, to satisfy the boundary condition, I might have a field mode that looks like this, okay? And then I could use that field mode to basically control this capacitor or something, okay? And then I could put one Cooper pair box over here. So it's a Cooper pair box here. Okay. I could also put another Cooper pair box maybe over here, so that both of them are maximally coupled to the field here. Okay. So once we've done that, and then we use this. These are the external links. Okay, so maybe this is connected to the gate of Cooper pair box 1. Okay. This might be connected to the gate of Cooper pair box 2. Okay. So this is box 1, box 2. By controlling this gate voltage, I can tune the resonance frequency of this Cooper pair box into resonance with the cavity mode. So certainly by controlling electrical signals, it's much easier than controlling atoms. So at time t0, I could tune this thing inside into resonance with the cavity, and they undergo this James-Cummings dynamics. Okay, and then at time t1, by using electrical signals, I switch this out of resonance, I switch this into resonance, okay, and continue this resonance until time t2. Afterwards, I switch both of them out of resonance with the cavity, and then now these two Cooper pair boxes have been entangled. Okay. So maybe we can go back. We talked a little bit about Josephson junctions before, right? But we didn't get enough time to talk about Cooper pair box. Maybe we could return to that, okay. Or I could give you guys something to read on this matter. Okay. So that's a side note of how one of these systems could be realized. But now the problem with this is, although this all looks very fancy and stuff, it looks very nice, but really, this is not really a good entanglement that we can use. Because right now we've only entangled 1 degree of freedom, which is the internal degree of freedom of the two atoms. Right? The two atoms also have degree of freedom in spatial and spin. Those are not entangled. And if we really wanted to entangle two atoms, we want to entangle all of those degrees of freedom. It's such a simple case, we cannot do it. There are more elaborate schemes.